Hi, my name's Alex Novikova, and I'm a grade 12 student at Bill Carruthers Secondary School, currently taking advanced functions. In this video, I will be leading you through a step-by-step process in order to answer a textbook question in its entirety using grade 12 concepts from this course. This video is especially for those students out there who weren't in class for lesson 9.3, Combining Functions Products. I'm here to help. So up next, I'm going to read the question for you guys. A water purification company has patented a unique process to remove contaminants from a container of water at the same time that more contaminated water is added for purification. The percent of contaminated material in the container of water being purified can be modeled by the function C of t equals 0.9 to the power of t, where t is the time in seconds. The number of liters in the of water in the container can be modeled by the function L of t equals 650 plus 300t. And it asks you to write a function that represents the number of liters of contaminated material in the container at any time t, and to estimate when the amount of contaminated material is at its greatest. I would also like to point out that there are two different functions to consider in this problem, not just one. This is actually a very important concept to note because it will come up later on. I also want to introduce the concept of IROC, which is the instantaneous rate of change on a graph. It is calculated at one moment in time, for example at 3 seconds as shown here. We would draw a tangent that just touches that point in the graph and its slope would be the rate of change. When a graph changes direction, the rate of change or slope of the tangent should be 0, and this is how we will verify our final answer to this question. AROC, on the other hand, is fairly different. It is when we calculate the average rate of change over a certain period of time. After stepping back and looking at the big picture of this problem, you can see that it is actually fairly simple. The premise is that this new process to remove contaminants from a container of water involves two actions. Contaminated water is being added as the contaminants are being removed. There is only one major connection that needs to be made in order to begin the process of actually finding a solution. The question asks for one thing only, and that is to estimate the time at which the contaminated water is at its greatest. In other words, we must determine the maximum point of the function. And that's all there is to it, really. In order to complete this problem, we will need to follow 4 simple steps. Number 1 is going to be finding the combined function by multiplying our two given functions together. Number 2 will be actually graphing the function using graphing technology. Number 3 will be identifying where the maximum point lies on the graph. This will be where the amount of contaminated material is at its greatest. Number 4 will be drawing a tangent through the maximum point and calculating IROC at that point in order to verify our final answer. Now, you may be wondering, what exactly is a combined function? Well, it's exactly what it says it is. It is when you combine two different functions together, and in the specific case of this problem, we are multiplying them. We do this so that we can create one function that models and takes the two separate ones into account. Graph 1 shows the number of liters of water in the container as a function of time, and it is a linear relationship. Graph 2 shows a percentage of contaminated material as a function of time, and it is an exponential decay relationship. You can see it is quite evident that the final product of the two beginning functions, or the combined function, is a combination of them, and is used to answer the problem. Now that we have a thorough understanding of what the problem is asking us to solve for, we will dive into the more specific details on how to solve it. Step number 1. Create a function that represents the number of liters of contaminated material in the container at any time. I previously mentioned that it was important to understand what each separate function modeled because it helps when finding the combined function. If you were trying to find the number of questions you got right on a test, you would multiply your percentage mark by the total number of marks on the test. You can see that this idea relates to the problem directly because the percent of contaminated water multiplied by the number of liters in the container will give you the amount of contaminated water in liters. This shows why it makes sense to multiply the two functions together to get the final one. The final combined function being C of t times L of t, which is m of t equals 0.9 to the power of t times 650 plus 300t. Our second step is going to be using graphing technology to graph the final combined function. We have to make sure to choose an appropriate scale in order to be able to spot all of the important points and asymptotes and make sure to label each axis accurately. Y-axis as contaminated material, and x-axis as time. And now we are on step 3. This is where we identify the maximum point of the function, which is where the contaminated material is at its greatest. The x-coordinate of this point represents the time in seconds that the material is at its max. From the graph, we can identify this point fairly easily, and that is 7.325, and the y-coordinate is 1316.104. And there you have it, you've solved the problem. But you might be wondering, wait, when are we going to use the grade 12 concept? Now, that's a tricky question for me to answer because you technically already have. You just didn't realize it. The instantaneous rate of change is what I'm talking about here. If we didn't have a graph to look at, we wouldn't know whether or not what we identified as the maximum point actually is the maximum point. The key idea that you must understand is that a maximum point on a graph, or for the purpose of being general, the vertex, the IROC will be 0 because it is where the graph changes direction. At the exact point that it changes direction, the tangent will be horizontal, which means the rate of change will be 0. The IROC of a function is dependent on the x value at which it is calculated. This means that it is constantly changing on a curved line. It's simply just the slope of the tangent that touches the point. For example, the IROC would be a positive number at 1 second. This is because the graph is going upwards or increasing. The IROC at 2 seconds would be a negative number because the graph is going downwards or decreasing. In order for us to be sure we have truly identified the point at which the contaminated material is at its greatest, we can solve for IROC at the max to make sure it is 0. All we have to do is solve for the slope of the tangent using the equation y2 minus y1 over x2 minus x1. We can find our x1 and x2 values by adding 0.001 and subtracting 0.001 from the x value where we want to find the IROC. In this case, we are using the maximum point, 7.325. Then we will plug these x values into our combined function to get our y1 and y2 values. The reason why we add and subtract 0.001 is to get 2 points that are extremely close together in order to use the slope equation, which we can now plug our x and y values into to get our slope. Please do not be silly like me and remember to include units. Here they would be liters per second. The final slope won't be exactly 0 because we use 2 different points to calculate it. But because we know this, as long as the value for the slope is extremely low, we can consider it to be 0 and therefore verify that the point that we have on the graph is indeed the maximum. And so our final answer is that the time at which the contaminated material is at its greatest is at 7.325 seconds. We know this because the IROC at this point in time is 0.06 liters per second, which is nearly 0. Before I finish up this video, I would like to bring to your attention a specific career in which this type of problem would be solved. That career is a water treatment plant and systems operator. These types of specialists work in water treatment plants. Fresh water is pumped from wells, rivers, streams, or reservoirs to water treatment plants, where it is treated and distributed to customers. Water treatment plant and system operators run the equipment, control the processes, and monitor the plants that treat water to make it safe to drink. These specialists also do similar work to remove pollutants and contaminants from domestic and industrial waste. Used water travels through sewer pipes to treatment plants where it is treated and returned to streams, rivers, and oceans. And with that, the video is over. Thank you so much for watching and listening. I hope you enjoyed, but most importantly, I hope you learned something. Thank you very much, and have a great day.
You see, stereophonic sound for the home is recorded on 2 separate tracks.